our next speakers from ARM, we'll have Srikanth Rengarajan, sorry for my pronunciation there, Manager of Automotive IP at ARM. And I think later on in the presentation, he'll be joined by Jinson Koppanalil, who is a distinguished engineer in the automotive group at ARM.
Excellent. Thank you. Welcome to our session on powering autonomous systems today. I'm Srikanth Rengarajan, and together with my colleague Jinson Koppanalil, I will be discussing the industry's direction of travel for self-guided machinery, to put it overarchingly, and also introduce ARM's high-performance processor of choice for this segment. Okay. Autonomous systems are headlined today by self-driving cars, but the reality is that the notion of decision-making without direct human intervention spans multiple applications. My own domain of responsibility spans industrial robotics, IoT, and smart manufacturing, besides automotive electronics. Electronic and electrical architecture, or popularly EE, are broadly used to describe the hierarchy and topology of the electronic systems within the vehicle. From a set of disjointed ECUs, electronic control units, today's cars are already being provisioned with integrated control units that co-locate the associated workloads within a functional or sometimes even a physical domain. The drivers are the same end-user benefits that drove the PC and server industries along the road to virtualization and integration, namely flexibility in the face of enhanced and uncertain workloads, as well as lower total cost of ownership. In the automotive domain, we refer to this kind of a consolidation by many names: domain controllers on the left, which is the functional aspect I talked about, and physical location is, of course, zonal controllers. Now, these benefits that I mentioned do come at a cost, the cost of complexity of design and verification overhead, which, when we're talking about mission-critical applications such as automobiles and industrial manufacturing, now have to include concepts like functional safety and cybersecurity. And this trend towards application consolidation and runtime allocation of resources are only accelerating, not just in automobiles, but also in the industrial sector. Dumb sensors and smart controllers, over-the-air control and configuration frameworks, software-defined X, where X could be automotive, industrial, whatever, logical and physical partitioning, they're all coming to the factory floor also, but without the affordability of downtime or a reboot in real time. This concept of industrial workload consolidation very much parallels the automotive domain consolidation, but at the same time placing sharp focus on meeting real-time or cycle time requirements. This broader picture here is one of coexistence, really. Mixed coexistence of mixed safety criticality, mixed real-time versus non-real-time, secure versus non-secure, effectively sharing resources on the same platform, but with different application requirements and attributes. And so what does this future demand from a compute perspective of all of us? Plentiful prototypes of autonomous systems exist today. I mean, just look at the scale of self-driving car testing across the globe. But unless we solve the algorithmic complexity involved and at a power and cost that's an order of magnitude lower than what is available today, these risk remaining just that, prototypes. So they need to respond to the application consolidation requirements outlined earlier, and also for the safety conscious domains of automotive and industrial electronics. Any such solution must provide system level resilience to field failures. Now, these failures that we talked about have been analyzed in other mission sensitive applications, and standards have been developed to address them with appropriate integrity classifications. The slide here shows some of these in some ordinal order of increasing performance and availability as the twin vectors of segmentation. On the far right, of course, is military and aerospace applications that both require high performance as well as high availability. And then there are other combinations from drones all the way up to robotics and, of course, automobiles. The automotive industry in this sense is already a decade old in terms of its ISO 26262 functional safety standard. But what is becoming clear is the need for survivability or availability, as we talked about, besides just awareness of failures. High availability compute is costly. The 3 out of 5 is what typically some of the more demanding applications on the right of the slide use, but that is a non-trivial implementation. But deployable autonomy demands nothing less. And therefore, systems we see emerging over the next 3 to 5 years will include support for not just fault detection, but also containment of the resulting error and associated migration of tasks to backup systems, for example. The path to such deployable autonomy lies in building in these redundancy features, these availability features into the system's building blocks. The benefits are twofold. System costs being traded off for development costs will result in significant savings using economy of scale, of course. Just think autonomous vehicles again. But also the scope, changing the scope of the component or IP level redundancy, that is cross-platform and cross-application. And now you're leveraging economy of scope. We at ARM have recognized this need for a while, and we introduced our first high-performance CPU for autonomous workloads back in 2018, the Cortex A76 AE core. Now that device exceeded our expectations in terms of industry welcome and applicability in meeting these challenges, but equally taught us the various dimensions of safety-related compute, namely support for heterogeneous compute architectures within a safety framework, the existence of a threshold cost per level of safety, call it ASILB for automotive or SIL for industrial, as well as system level safety considerations. Now, the recently launched Cortex A78A that we'll talk about in this presentation supports features that directly address these challenges. Firstly, the need for responsive performance is addressed, the 30% generational improvement, along with the concomitant power efficiency improvement. New modes of lockstep operation combined with support for cache line increase availability, talking to that requirement of survivability that we mentioned earlier. And system level integrity is realized via a set of interoperable AE cores that have been tested to ensure end-to-end reliability. And as with the previous generation, this IP will be certified as a safety element out of context by ARM within the applicable safety standards in automotive and industrial. Now, there is more value in this core in terms of configuration topologies, physical IP, and the like that people have come to expect, but I'll reserve those items for later slides. But for those unfamiliar with ARM's AE designations, but presumably have seen the Cortex A78 core that was released a few months ago, this slide should be instructive in terms of the differences. The fundamental microarchitecture is relatively unchanged between the two cores, but we do place a set of restrictions as well as mandatory enhancements to make these AE cores suitable for their AE class mission critical applications. Some of these are things like specific core counts, cache sizes, mandatory ECC protection mechanism on memories, etc. But equally, there are architectural enhancements that add value to targeted applications, like the ability to defend against return-oriented programming exploits would be one example of such a targeted feature deployment. More to the point, AE IP is designed differently to support safety features, such as the dual-core lockstep. This includes basic design hygiene, such as deterministic resets to avoid false positives, placement guidelines, and support for specific features like interface protection that were outlined earlier. The sum total of these differences are typically reflected in the safety claims that we validate through external assessment in our certification processes. And as I mentioned earlier, the AE portfolio is where this value is realized by our customers by integrating a set of predefined, architected, and validated IP that meets defined performance goals, while making it easier for our mission-conscious operators to be assured of certifiably safe compute systems. Here, portfolio refers to more than synthesizable design elements and extends to things like libraries, tool chains, debuggers, open source software, etc., that ARM makes available under the AE umbrella. But the journey to autonomous compute begins, of course, with the CPU, central processing unit. And I invite my colleague Jinson to walk through the details of the Cortex A78 AE. Jinson?
Thank you, Srikanth. Can you guys hear me?
Yes, I can.
All right. So in the next few slides, I'll walk you through the Cortex A78AE microarchitecture and discuss safety and scalability features of the core. So A78AE is a second generation design that we have specifically built for autonomous systems. So you can see a high level block diagram here. The key design principle behind the microarchitecture is to deliver highest performance at best in class efficiency. So that's both power and area efficiency. So compared to the previous generation A76AE, the A78AE is a wider and deeper out-of-order machine. The width and depth of the machine have been sized for efficiency. We've also made several improvements on the front end and the memory system to feed the core at high bandwidth and low latencies. Now let's dive into the microarchitecture details, starting with the front end. So one of the key performance features we've added is the MOP cache. MOP actually stands for a decoded instruction. So as the name implies, MOP cache is a decoded L0 instruction cache. It is smaller, but higher bandwidth compared to the L1 instruction cache. So when you compare the bandwidths, MOP cache can deliver 6 MOPs every cycle, whereas the instruction cache can deliver 4 instructions every cycle. So MOP cache fundamentally enables higher fetch bandwidth to the core. There are a couple of other benefits with MOP cache. First, the branch mispredict latency is reduced when the instruction delivery is out of the MOP cache, since we are bypassing the decode stage. Second, MOP cache allows us to do dynamic code optimization. In this case, specific code sequences can be automatically optimized in hardware to run more efficiently in the core. We've also made big improvements in branch predictor. So in the Codex A pipeline, the branch predictor is decoupled from the fetch pipeline. It's running ahead, hiding taken branch bubbles from the core. It also acts as an eyesight prefetcher, fetching lines that would have otherwise missed in the L1 instruction cache. So in A78AE, we have doubled the branch predictor bandwidth to 64 bytes per cycle, and it can also process 2 taken branches every cycle. So these improvements enable the predictor to run further ahead, providing even more fetch bandwidth and even earlier prefetches to the L1 instruction cache. So the MOP cache plus the branch predictor improvements provide a very high bandwidth and low latency front end. Let's look at the core. We have increased the rename and dispatch width from 4 to 6 MOPs per cycle. So that's a 50% increase in the width. We have also increased the out of order window by 25%. Now, both these changes help expose more instruction level parallelism and performance as a result. Let's move on to the execution units. So we have increased the integer execution bandwidth by 50%. So the key highlights are there is a new ALU, a new branch unit, a new multiplier doubling the integer multiply bandwidth. We've also added a second AES encryption pipeline. Let's move on to the memory system. So in the A76AE load store unit, it could support up to 2 concurrent load stores every cycle. So in A78AE, we've added a third load AGU and result bus. This allows more loads to be processed in parallel, increasing the load bandwidth by 50%. A78AE can also support 50% more in-flight loads and stores. This helps expose more memory level parallelism and performance as a result. One other area we've continued to invest is data prefetch engines. We have a number of prefetch engines that all work together, prefetching lines into L1 and L2 caches. So in A78AE, we've added new engines, one specifically for irregular access patterns. We've also spent a lot of time improving the coverage, accuracy, and timeliness of these prefetch engines. For example, we have an adaptive scheme that can track if the data is arriving late or early, and then can adjust the prefetch distance accordingly and ensure timeliness. We also have an adaptive scheme to manage aggressiveness of prefetch engines based on L3 utilization. Next, I'll discuss the functional safety features of the core. So in 2018, we introduced a split lock safety architecture for the cluster. So in the split mode shown on the left here, each core in the cluster is operating independently, resulting in the highest cluster level performance. Now, this is suitable for applications with low or no safety requirements. Now, it's possible to achieve ASILB or SIL2 in split mode. One way to achieve this is to run diagnostic tests periodically to check for any malfunction or failures. So if you observe the image on the left, we show the individual cores taken offline for testing. The downtime here is shown with the gray boxes. So one key thing to remember here is when the shared DSU logic is taken offline for testing, then none of the cores are available for use, and this leads to a performance impact. In the lock mode shown on the right, core pairs and DSU and its identical copy are run in lockstep. The primary logic and identical copy are performing the exact same operation and cross-checking each other's results. This is all hardware-based, no involvement from software. So this approach can detect 99% of the single point, transient, and permanent faults. This is ideal for ASILD or SIL3 applications, which need the highest functional safety. So in lock mode, we are trading off cluster performance for higher safety levels. Now let's look at the hybrid mode, which we introduced in A78AE. Here, the cores are running independently in split mode for the highest cluster performance. However, the DSU is running in lock mode, and we don't have to take it offline for testing. So DSU is always available, and there is always one or more cores for application use. Now, this improves CPU availability, and this is perfect for ASILB or SIL2 application. Now, the choice of split, hybrid, or lock mode can be made at boot time. This allows you to build a single SoC, and you have full flexibility for different use case of the design of the device. Now let's look at the key elements of functional safety. Going down from top right, to enable lock mode operation, we have a redundant copy of the core and the shared DSU logic. Now with any redundant logic, we need to make sure it boots up exactly the same state as primary logic. To achieve this, we have added mechanisms to enforce a deterministic reset. Also, the redundant logic is time shifted. This is to protect against common cause failures, which can affect both cores in the same way. We also have comparators on the core and DSU outputs to detect any divergence between primary and redundant logic. Now, going down from top left, the L1, L2, L3 caches all have memory protection, either ECC or parity. Now, normally, a permanent fault in either L1 or L2 in a locked pair will result in a divergence. To be resilient in this case, the A78AE course allows you to disable faulty regions of L1 or L2. And this increases the availability of the core even with permanent faults. Now, all the external interfaces of the core have interface protection, and it can be extended to rest of the SoC as well. Next, let's look at the scalability features of the core. So A78AE is highly scalable, and you can build a wide range of cluster configurations at various performance and PPA targets. So we offer a variety of L1, L2, and L3 cache sizes as shown on the slide. In a single cluster, you can have up to 4 A78AE cores or 2 core pairs. You can even optionally add our high efficiency A65AE cores the same way. So the diagram here shows the smallest and the largest clusters possible. So in an SoC, you can group together 8 such clusters using CMN 600AE, which is the coherent interconnect from ARM. This could be a mixture of compute, GPU, or other coherent masters, depending on the system requirements. Next, let's look at the area efficiency of the core. So here is a floor plan view of the A78AE core pair. It is 15% larger, but it's delivering 30% more performance and much more area efficient than A76AE. Now let's look at the power efficiency of the core. So here is a performance per watt comparison between A78AE and A76AE. So the y-axis shows spec-in 2K6 performance, and the x-axis shows the power consumed to deliver that performance. So the orange is A78AE and the green is A76AE. So in this graph, higher is better. It means more performance for the power consumed. So as you can see, A78AE is doing really well. It is delivering 30% more performance at the same power efficiency as A76AE. Now at a fixed power budget, A78AE is delivering 25% additional performance. At a fixed performance level, it is consuming 60% lower power than A76AE. So wrapping up, so we are really excited about Codex A78AE. It is a fundamental building block for next generation autonomous systems. It provides 30% more performance at best-in-class efficiency. It has all the required features necessary for safety-critical applications. And these safety modes can be configured post-silicon to match the use case. A78AE is highly scalable, as you have seen, and it can be used to build the whole range of autonomous systems. So that's our presentation. Thank you very much.
Thanks, Jinson and Srikanth, and we'll see you in a bit in the panel discussion.